Hello, everybody. There's always a few people that say hi back. So, my name's Chris Murphy, and I'm an Unreal Engine evangelist. Now, my job is helping developers, typically across Australia, New Zealand, and Southeast Asia. I basically head around, I help out different studios, and where possible, I try and let people know either what's coming or little features that they may not be aware of or how to achieve certain techniques inside of Unreal Engine. Now, for any of you that have seen me present outside of Korea, you're probably aware that I'm usually very, very, very hyperactive, but I'm going to do my best to have a slow, easy session today so I'm not speaking too quickly, and hopefully the interpreters can keep up. So today we're going to be focusing on Niagara, which is Unreal Engine's new real-time visual effects system. Now, out of curiosity, who here in this session currently has experience with Unreal Engine's existing VFX system, Cascade? Raise your hand if you have. Wow. Okay, that's actually a pretty good percentage. I'm happy to see that, because I wasn't sure how it'd sit. So, is that coming through okay? All right, so for today's session, we're going to be focusing on building something reasonably interesting. We're going to be working off of Unreal's... So, what we're going to be doing today is we're going to be building a holographic map that sits inside of this region here, okay? We're going to be building something that is going to be a three-dimensional holographic map. Now, we're going to be using Niagara for this, and there's a few things that we're going to need to do along the way. But first off, I want to begin by just explaining what Niagara actually is and why we're focusing on it. Now, to begin with, when it comes to Unreal Engine's existing system, Cascade, it's particularly good at achieving high-end quality effects. It's useful for making explosions, it's useful for making smoke, it's useful for making all of the things that we've seen inside of games before. But with Niagara, Unreal's new system, it's actually much better at kind of processing things in almost an ambiguous way. It can be used generally for just processing large data sets. And the fact that we choose to use that information to blow things up or create fire or explosions or whatever is our choice. And hopefully you'll see that coming through. So first off, we're actually going to quickly look at enabling Niagara. By default, it is disabled because by default, it is considered an early access feature. Now what that means is it's currently in a situation where we're cool for people to play with it and give us feedback and start experimenting. We just don't consider it quite stable enough yet for release, okay? So it's getting very close and it's worth starting to learn this tool. It's especially worth starting to learn this tool if you're a student, because by using Niagara, you can create a ton of effects that no one's ever seen before. So, by default, it's disabled. And I've already gone ahead and enabled it. And if you want to turn it on, it's here. Now, it's also worth noting that we have Niagara Extras. Now, Niagara Extras is additional content that is too experimental to really include in the official Niagara plugin. But if you're generally kind of poking around at Niagara and trying to work out what you can do with it, this extra plugin might be worth enabling to just see what content is there, because there's some pretty cool stuff in there. Now, I'm going to right-click, I'm going to go to FX, and I'm going to begin by creating a Niagara system. But I want to quickly raise that this is the first point where most developers start to get very nervous. If you've never touched Niagara before and you go to the FX menu, you're going to see Niagara dynamic input scripts, Niagara emitters, Niagara function scripts, Niagara module scripts, Niagara parameter collections, Niagara parameter collection instances, Niagara systems, and that is a whole lot of Niagara stuff that we haven't learned yet. So my advice here is that when you're first learning this, just initially focus on Niagara system, okay? You're going to confuse yourself if you look at everything else. Just acknowledge that it exists and move on with your life and just go to Niagara system for the time being. Okay? Now, when I go to Niagara system, I can base it off of an existing system template, or I can base it off of one that already exists in my project. In this situation, just to demonstrate what Niagara is, I'm going to base it on a template called Simple Explosion. And I'm going to call this FX Explosion. We're just going to open this up. And now this is seeing Niagara for the first time with unbuilt shaders. One moment, it'll catch up. So, when we first see a Niagara effect, this is what we have. Very loud noise. Go away. So, this is what we have. Now, if you're used to Cascade, let me explain what you're looking at. Over on the right-hand side, you'll see that we have a module stack. This on the right-hand side is very similar to what you used to see in Cascade when you used to have column after column of emitters. Okay? And each of these represents a different emitter. So instead of having all of them next to each other, they're now just housed inside of separate assets here. Okay? Now, the strength in doing this is emitters themselves are actually separate assets. So if we want to, we can create a spark emitter and then share that emitter across every single explosion and electrical effect inside of our game. Now, the reason it's really useful having this kind of this compartmentalization of functionality is that pretend you were working on a fantasy game, okay? If you, in your emitter, got magic looking really, really, really good, you could use that same magic emitter in all of your fire magic, all of your ice magic, all of your, I don't know, other magics. And you would just override the little bits and pieces for those specific effects, but the magic itself would still see consistent across every effect. And if you ever modified the base emitter, those changes would propagate to every other emitter in every other system. Okay? And this is a great way of ensuring that your projects have a general layer of consistency across it. By the way, my apologies for the people just here. I feel like I'm just creepily peeking at you over the monitor. So what we're doing here is, let's have a quick look at how this works down below. Now, the first thing I want to get across to you is we can pause the emitter and we can slowly play it through to change our variables, okay? But under each property here, we can actually override anything we want to. So if I wanted to override my lifetime and set that to 1 second, 2 seconds, 3 seconds, I could do that. If I wanted to override my mass, I could do that as well, okay? But one thing that's very useful whenever you're starting off on an emitter is this little variable called determinism. Now, if I enable determinism on every single emitter, one after the other, here's what we get. I can not only play my effects forward in time, but I can now play them backwards in time as well. So I can look for my emitter at any specific point and then go to a single variable and say, hey, what would you look like if the initial velocity burst was a much higher number? Oops, higher number. So we can actually see that the entire system stays the same, and we can control these variables as we see fit. And this is really, really useful, because I'm sure many of you that have already been using Cascade are aware of that system where you would change a variable, mash spacebar, change a variable, mash spacebar, and you'd be like, trying to look at the explosion again and again and again. This person gets me. So, this is a nice way to kind of get around that, and you can much more easily customize exactly what it is you want to create. Okay? Now, I'm going to scrap the explosion. I just wanted you to kind of generally be aware of what we were doing. But just before I get rid of this to work on the actual effect, I want to show you one more very important thing. Now, if I look at this on the right-hand side, I can see that we have, just going to minimize these, I can see that we have system, emitter, and particle brackets. So see how we have system spawn, system update, emitter spawn, emitter update, particle spawn, and particle update, and then down the bottom renderer? The reason for this is any instructions in system spawn are processed with the system, when the system ticks. Anything in emitter spawn means that this specific emitter will process information as necessary. And it can feed that information to the rest of the system. And particle spawn is every single particle will run this series of instructions when a particle is created. And particle update is every single tick that a particle is being processed. Each one will process this information as necessary. Okay? Now, I know I'm kind of hitting you all with a lot of information, but hopefully this will make a little bit more sense as we move into the next phase of the talk. So with what we have right here, I want to quickly touch on one last important thing. So notice we have a variable here called gravity force. Okay? If I double click on any module in Niagara, this is what I'm greeted with. Every single module in Niagara is actually its own node graph. So it's actually a stack of node graphs. Now what's really interesting with this is if I zoom in on just this module for a second, we can see that we've got, it's saying, get me the values for physics.force, module.gravity, the coordinate space, and the particle mass. Now what's really interesting with these values is that if gravity hasn't been set, this is the value it will create. If there is no physics force that's already been created, it will create a physics.force variable and set it to 0, 0, 0. If the particle currently has no mass when this node is called, it will give it an initial mass of 1 and process that. Now what's really cool is that this information is completely arbitrary. You can process information in any way you see fit, and you can call those variables anything you want to, which means if I look at gravity force, I can see that it's multiplying gravity by my mass, it's then applying that to the current force, and it's setting physics force and a physics gravity vector. And eventually, inside of this system, we have this node called solve forces and velocity, which literally just adds all of the forces that have been calculated, which adds all of the forces that have been calculated, puts them all together, and changes the particle's position accordingly. Now, if you think about this, while yes, I am using this for physics right now, there's nothing that stops you from creating a series of modules that are specific to your game. So let's go back to that magic example that we had before. There's nothing that would stop you from having a series of modules that add up all of the different types of magic that that spell is using to process them into a specific emitter that at the end create an effect that is the combination of all of those different types of systems. You know, I could create a particle.ice magic level and then change that to any value I wanted it to be. You know, I can create all sorts of systems. Alternatively, for another project, I could create an emitter.heat and use that heat variable on every module to process so that the heat makes the particle jitter more, or maybe it makes it more stable, or brighten up, or do whatever I see fit. But functionally, this is very similar to Cascade. The only difference is in Cascade, it was always the position, it was always the color, it was always very specific things. But in Niagara, we can make any value that we want to, and we can bind that information to anything else. Because this is the last little bit that I want to show you before we move on to the actual effect. I can add renderers, so I can actually have multiple renderers on any emitter, okay? Which means I could render sprites and meshes in the same emitter. Not only that, but if I scroll down here, I can see that position is bound to particles.position. I can see the color is bound to particles.color. Okay. Now this means that I could have two emitters that are using 95% of the same data, except the last emitter gets the current position and orbits around it. So I could have two sprite emitters on the same thing that can create an interesting effect. But the interesting thing here is that all of that information that we would be processing, all of that information is completely arbitrary, and it would only be being processed once. And the two separate renderers would be sharing that information. Now that's really, really valuable, because if you're clever with how you make these effects, You can share large chunks of information and pass them between different renderers to create some really, really special high-fidelity effects with very minimal overhead. So let's stop that for a moment and let's go make something cool. I'm going to right-click, I'm going to go to FX, and this time I'm going to create a Niagara emitter. Okay? Now, a Niagara emitter, as I said, is a standalone emitter that gets brought into a system. And I'm going to base mine on a fountain. And I'm going to call this circular spawner. Now, circular spawner, to begin with, is just going to look like this. Okay? Now, what I want to do is I want these particles to spawn in a circle, as the name implies. So to begin with, I'm actually going to ditch all of the things that this fountain has. I don't need to have any of the forces. One thing that's worth noting is watch what happens when I delete solve forces and velocity. See these drag modules and gravity modules? They actually throw an error because for them to function, they require solve forces and velocity. And in your modules, you can set custom dependencies. You can say this module needs to eventually be something that exists. Or alternatively, you can say this module needs to exist before me to do something. But I'm going to scrap them. We're going to have our particles looking like this. I'm also going to get rid of sphere location. And I don't need to calculate our size by mass, so I'm going to disable anything to do with mass. Now in my particle spawner, I'm going to add a cylindrical location, which is going to spawn my particles in a cylinder. Let's increase the spawn rate so that's a little bit more visible. Particles. Okay, so what we have here is I now want to make it only around the outside of the cylinder. So I'm going to get this, and I'm going to say surface only. And if I move my cursor inside, you can see that we're now only spawning the particles on the outside of the cylinder. I'm also going to disable the end caps so that we end up with something that's thin. And finally, I'm going to set the height to be 10 centimeters, and I want this to be a reasonably wide ring. Okay? So we've got something that now looks like this. Now I'm going to apply this and save it, and I'm going to move on to creating the actual system. It's worth noting that I didn't have to create this way. It just is purely for the sake of me demonstrating that an emitter, when I right-click on this, can be put into a system. So you'll now see that as a system, I can no longer delete those nodes. I can disable them, but I can't delete them, because the system is taking its information from the circular spawner emitter. Okay? So in this situation, I now need this to be, if this was going into the middle of my office here, I would need this to be in the middle of this location. Okay? So first thing I'm going to do is I'm going to select this, I'm going to copy the location, I'm going to go to here and I'm going to paste the location so that it's centered. Now, this is clearly the wrong size. We want to have something that's reaching the edges of this effect. So it's worth noting that if you go to an orthographic viewport, you can use your middle mouse button as a ruler to see how big this is. So see, I can drag that up. Now this is 470, 480 centimeters. So I'm going to set this to be 480. And back in the office, we can see that's reasonably snug. Now, I also want to create a holographic map that's up, my bad, a holographic map that is up here, okay? But I want the ring to be down below. So to do that, I'm just going to set an offset on my cylinder location to be negative, let's say 150 units. Okay. Great. Now, I want this to be a series of particles that project a texture onto them. So if we look outside, I have this drone, okay? And this drone is capable of flying around. And when it does, I want a texture to be displayed on these particles, okay? So the next thing that I'm going to do here is I'm going to, if we were to display an image on particles, Pretend that we had all of the particles in a grid, okay? If we had all of the particles in a grid, this coordinate would be 0, 0, and this coordinate would be 1, 1, all right? Because it's a UV. Now, what we want to do is give every particle that we spawn a random number between 0 and 1 and store that as the information so that it knows which pixel to look at from the image that's going to be popping up on it, okay? So to do that, what I'm going to do is in my particle spawn, I'm going to say when you're created, I want to create a vector 2D. And I'm going to call it particles.uv. Now I need to set this value to something, okay? Now, I can literally just click here, and I could type in a number, but I could also just type in random. Because any input to any module can actually be its own sub-function known as a dynamic input. You can roll your own sub-functions here, which are excellent. So that's a Niagara dynamic input. And this is now a value between 0 and 1, okay? Now, if I look at this, how do I know that's working? Well, if I go to Window, and I go to Attribute Spreadsheet, I can click Capture, and this will show me every single attribute and what it's currently set to for every single particle at this given moment. And I can see that uv.x and uv.y are all random numbers between 0 and 1. So we know this is working. Now, the next thing for me to do is let's preview a texture on these particles, okay? Now, I'm going to be a little bit cheeky, and I'm just going to set, for the time being, I'm going to set these particles to have a position that puts them in a grid, just so I can see the texture. So I'm going to set particles.position. Now, when I set the position, I can set this in any number of ways. But it's worth noting that sometimes writing code is easier. Now, I could do what I'm about to do in a node graph, but sometimes writing code is easier. Not always, but sometimes. And there's nothing that stops me from writing straight HLSL into this and typing float3, we're going to get particles.uv and set 0 and then multiply that by 400. And what we're left with is this. So I can just write straight HLSL into this, okay? Now what this just did is this set their position to be a value where x and y were equal to the uv, so 0 to 1, and it set z to 0, and then I multiplied those numbers by 400, which means any value that was previously 1 is now equal to 400. Any value that was previously equal to 0.5 is now equal to 200. Do you get what I mean? Like we've created a square. So let's preview the image on this. I'm going to go down to my particle update, and I'm going to add sample texture. And I'm going to bring this up to here. Now when I get my sample texture, it's going to know which texture to use. I'm just going to set this to be the demo logo. Next up, it needs to know what the UV data is. And I'm literally just going to bind this to the one that we just created called particles.uv. Now this isn't going to work for two reasons. First off, if I look at my sample.texture, you'll see that it's actually getting the texture and saving it to a thing called sampled color. It's not actually setting the color, it's just getting the color data and storing that in a variable for us. So if I go back to here, if I wanted to, I could just bind the current color to be output sample texture sampled color. And that will bind to the node above us. Now the next reason that this effect won't work is because it's currently a CPU particle, and we're only able to access that information if we're in a GPU particle. And you'll notice that when I switch this over, this is what we get. So we're now accessing the texture data and we're pulling this straight in, okay? But let's do something way cooler. Next up, first off, let's increase the spawn rate so we have way more particles. Now the next thing that I want to do is, if we look at this drone that we had outside, this drone, if I look at the blueprint of it, oh, I have translucent selection enabled. If I look at this drone, it currently has a camera on the bottom of it that is known as a scene capture component. So it has a camera flying around the world capturing color data and alpha data. Now if we look at what that's doing, I want you to look at this here, this image. Watch what happens when I run the game. Okay? So if we look at this image, you see what's going on? This texture is created by the drone's camera flying around. So what would happen if we got our map, and instead of loading in the Unreal logo, what if we set the texture to be the camera? Okay. And if we were to look at this, give it just a sec. So where's my drone? Oh, sorry, I didn't set it to real time. There we go. So if we were to look at this, it might be a little bit tricky to see on this screen. There we go. So see how that texture data is actually moving with the drone? Now, here's the interesting thing. If we know where something is in space that's taking an image, and we know the shape of the lens, we're actually able to reproject those particles back into the world by saying that this pixel is this far. Because remember that our image right now, the alpha channel, is capturing depth. So we can actually reproject those depth values to create something in the world. So let's go ahead and do that. I'm going to get this, and I'm going to say to this system, recreate camera projection. Now, it needs to know a few things. First off, it needs to know the depth value. Now, remember I said the depth value is being stored in the alpha channel of our camera? So let's float from color. The float is going to be the alpha channel, and the color is going to be the color that we're pulling from the sample texture. Okay? It now needs to know the field of view, which is default 45, and it needs to know the projection, so where it is on the UV. So once again, I'm just going to bind that to the value that we've already got. Now next up, I need to tell it to project downwards. So I'm going to set this to be a value of 0, 0, -1, 0, 1, 0, and 1, 0, 0. Now, if we were to look at that back here, just for one moment. Now, it's hard to see anything right now, and the reason for that's actually kind of interesting. If I drag this out to here, that's the system. Whoops, it's getting cold. That's okay. If I run the system, the world is actually now being recreated as particles because they're being reprojected. Now, this system is way too big. It's huge, okay? And the reason that it's huge is right now we have an equal mapping so that the camera, as it's projecting into the world, if it's 1,000 units away, that particle is also 1,000 units away. Do you get what I mean? And if like that particle over here is 2,000 units away, this particle is 2,000, which it makes for a very, very big projection. So what we need to do is pull these particles. First off, we need to set them so that they are at the same height as the emitter. So see the emitter's all the way up there? So I'm just going to subtract a value as an offset and move the whole system upwards, okay? And after I've moved the whole system upwards, I'm going to scale it into itself to squish it down so that we can put it in the middle of our projection. So let's begin. Now there's a few ways I could do that, but honestly, the nicest, cleanest way is probably for me to go ahead and create my own Niagara module that's called Adjust Camera Projection, okay? So I'm going to go back to here, I'm going to right click and go FX, and I'm going to create a new Niagara module. And I'm going to call this Adjust Camera Projection, okay? Now camera projection, it's going to need to know a few things. First off, we're going to want to get the current position, so I'm going to add a vector, and I'm going to call this module.current position. Okay? So I need to know the particle's current position. Now I need to offset this by something. So I'm going to make another vector that's going to be called module.offset. Okay? And if I want to set these to something, all I need to do is get my current position, subtract the offset, and I'm going to set this to particles position. So I'm just going to set the current particle position directly. Okay? Now if I go back to my holographic map, you'll notice that under update, if I was to type in adjust camera, that's now a node. And I'm going to set the current position to be equal to this camera projection's output. Now, it's worth noting that this camera projection, because of this checkbox, it both sets the current particle position, but it also sets an internal value to say where the projection was, okay? So I'm going to uncheck that, and I'm going to set this position to be equal to the camera projection's output position. And you can just start typing in the name of the module and it will tell you all of the outputs available. Now the offset is probably like negative, I think like 4,000, give or take. And if I look back here in the world, we can now see that that's reasonably well situated around the emitter. So this is now much higher. And we've started to get something here, okay? So we're looking a bit better. We can start to see the world. The next thing for me to do is squish it into where it is, okay? Now, imagine for a second that the particle's position, the middle position, imagine for a second that it was located at 0, 0, 0, okay? Now, if I knew how wide this particle projection was, and I divided by that number, let's say it was 5,000 units across. If I divide it by 5,000, I'm now going to have a value between 0 and 1, okay? And if I multiply that by any number, say multiply it by 400, any particle that used to be at a position of 5,000 is now going to be at a position of 400, because 5,000 divided by 5,000 is equal to 1. 1 times 400 is equal to 400, okay? So this is a good way for us to squish it inwards and then readjust the size to whatever we actually want it to be. So in my camera projection, what I'm going to do is I need to know one thing first that we haven't established. I need to know how big this system is. Now here's the cool thing. If I use the power of math, we can actually work this out, okay? My apologies for this being written in English. I should have thought ahead. So, if you know that the camera is located at this position, and we know that this was 4,000 units because we offset it by 4,000 units, tan of this angle is equal to opposite divided by the adjacent, which means tan of this angle multiplied by adjacent tells me this distance, which is how wide the camera projection is at that given location. I feel like maybe 10 people in this room got me, but hopefully that's enough. Just magic. Okay, so that means I need to know the angle, which is the lens angle, and that's about it. So I'm going to go to here, and in my camera, I'm going to say I need to have a float called module.cameraAngle. Okay? Now remember, to do this, I said that it needed to be done as if it was towards 0, 0, 0. Like I need to divide it as if the midpoint was 0, 0. I can do that by transforming this position into what's called local space, and then working it out in local space and converting it back to world space. So to do that, all I need to do is get this and type in transform, and I'm just going to transform the position. And I'm going to go from world space to local space. After I go from world space to local space, I have to divide this position by the length of this offset multiplied by oops, no, not that, tangent. Much better. Whew, that would have been bad. Okay, wonderful. So I'm just multiplying these two things against one another. Okay, I'm going to divide this by that. I now need to have one new variable, which I'm just going to call vector size. I need to create a new vector called new size. And I'm going to default that to 400. 400. 400? Do they translate my screams when I say, Okay. I'm now going to multiply it against the new size. Okay. And I'm going to convert this from local space back to world space. It's worth noting that you can actually convert it to simulation space, which allows this to be a checkbox that's done inside the particle system. But I'm just going to keep this straightforward for the time being and go from local to world. Okay? Now, in theory, assuming that I didn't screw anything up, if we look at a holographic map in the world, we've now got that. So we can see that that's working. That's squished it down just the way that we wanted it to. Okay? Now, it's really, really bright. So I'm going to shrink my particles down as well, because that's not very pretty. So I'm just going to shrink this down. I'm going to set the particles to be a size of just maybe 1 centimeter. There we go. And you know what would be nice? Let's have way more particles. So let's add a 0 onto that. All right. So we can now see that we've got ourselves a holographic projection that's moving through the world. But we can make this way cooler. Okay? Because what if instead of just setting the particle's position, because of how Niagara works, everything is arbitrary, right? And because everything is arbitrary, if instead of setting my position through this adjust camera projection, if I saved this to a variable called particles.projectedPosition, okay, so I'm making a new variable and just saving the final positions into that data. Here's the cool thing. There's nothing that stops me from getting this position and saying in the update loop, I want to set the particle position, but I want the actual particle position to be a smooth lerp that is my current position, and it's moving towards my projected position. Okay? And what this creates, let's put this back in real time, is this. Now that may look a little bit weird, but all of our particles start as a square. And if I increase this rate, those particles are flying up from the square to create my system. In fact, if I was to turn off the square projection that we created, they would all start in a ring. And if I look back here, my particles are flying from the edges to create a projection. And the cool thing is my convergence rate tells the particles how fast they could move. Do you get me? Which means when the system moves, I'm updating their new particle target, but the particles themselves have to still move to that new location. Okay? So this is something that's quite cool. We can make effects that no one's ever seen before, because this straight up looks like something out of The Mummy. Okay? But we can do something way cooler. Okay? We can do something way cooler. Let's get this effect, and imagine if the particles, before they took off and moved to their final position, convergence rate is really just another variable, isn't it? And because convergence rate is just another variable, there's nothing that stops us from saying, let's get convergence rate and set this to a curve. And let's set this so that maybe over the course of their lifetime, maybe the particles are really slow when they're first created, and then over the course of their lifetime, they get way quicker. So if I got this, I could say at the very start, you have a value of 0. You don't move. And we can now see the particles are chilling out. I could say that at this far into your lifetime, the particles start moving. And notice the curve is keeping them in place for a while and then moving them around. And the cool thing is I can shift this so they stay there for a while and then eventually zoom out. And I can scale this by whatever number I want. And if we look back at this system, the particles are now spawning into existence over here. And a really cool thing is that if I run this in slow motion, see this little red particle? They are actually going to their positions in the world. So this little red particle, if we follow it, or this orange one, they're spawning and they know where they're going because they already know what their color is going to be. And in turn, we're left with something that ends up looking like that, which is pretty cool. So I'm going to stop the sim. So you can see that we're starting to be able to create some really, really interesting effects. And the exciting part of this is that this really didn't take too much time. I know I did some, I was pulling out math and whatever else because I'm a tech artist. That's what I do. But the thing is that you could never have created an effect like this in Cascade. It would just be impossible, okay? And when I look at something like this, there's nothing that stops me from getting any value that we currently have and changing it to whatever I want to do. Like, before I grab before I change the color, right? But what's to say I don't get the color and start it off so that at the beginning of its life, every particle is invisible except for green. And now, over the course of their life, these particles are going to gradually get less and less green. I can move this all the way back. And I can even rebind. This curve index is bound to a normalized age. But there's nothing that stops me from making that normalized age like a heat variable or something else that was being read in. Like this can be bound to anything. I'm really just passing numbers around into instructions that are doing whatever they want to do. This would look better if it was a little bit brighter. That's the stuff. Like we've now got this cool little area where these green particles are spawning, and they're all going to react to the world in whatever way they need to. They're going to physically move up and down, and I can change their convergence rate at a moment's notice. I can set this up to be whatever I want it to be. My apologies to the interpreter. I'm clearly getting excited and speaking quicker. So, if I up the convergence rate, these particles move way quicker, but we can still see them doing an interesting effect of moving up and down. But my point is this, is that in Cascade, this effect just wouldn't have been achievable. It just would have been straight up not a thing you could do. If someone wanted to make this effect in Cascade, historically speaking, typically what they would have done is looked at it, shook their head, and made it with a 3D mesh out of a bunch of cubes instead. A bunch of transparent cubes. And their art director would have been a little disappointed, but they would have been like, I guess that's okay for our 3D map. Because it wasn't achievable. The thing is that now when you hit something that you can't do, it's much more of a situation of you saying, should I spend some time and write some modules to do this? Or should I not do it? Rather than the previous situation, which was, well, I guess I'm not doing that. And this to me is much, much, much more valuable. And this is why it's really exciting, is because, as I said earlier, Cascade is great at making explosions. There's a reason that Cascade has pretty much been the same thing since like UE2. It's like 15 years old. But there's a reason that it's pretty much stayed the same. It's very good at what it did. And historically what it did was explosions and smoke and fire and sparks and magic, and all of that stuff looked good. But the truth is that when you have a system that isn't inherently bound to being a system to make explosions and fire and smoke and sparks, you're going to be doing things that I don't expect you to do. You're going to be adding new renderers, maybe metaballs or something, to get cool volumetric rendering out of a particle system. This opens up so many doorways, and the reason I'm excited isn't for the new explosions. I'm sure they'll be cool. The reason it's exciting is you're going to make stuff that I've never seen before, and that I won't have even expected to see in a video game. And that personally makes me really, really excited. So thank you very much for your time. I hope this was useful. We're now going to have a brief Q&A. Thank you.